warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. My name is Azarima, and I'm honored to present our research, especially on wave conversion energy, especially which the title is numerical simulation of effect the geometrical underlip on the performance of oscillating water column. So on this occasion, we will explain with some content in today. And the first is introduction, and second is material methods, and then wave generation method, result and discussion, and then conclusion. For the introduction, oscillating water column is the device that developed for converting sea wave energy into wind energy using a column. So this wind energy can convert into electrical energy with directional turbine. And according to the data of Dewan Energi Nasional 2019, Indonesia has a potential sea energy of 61,000 megawatt. It's quite large. However, with such a huge potential, in Indonesia, the utilization of sea with energy is still 0%. Still, it's very relevant because of sea development, it's costly, but the output is not sufficient. So it cannot be an option for the government from that point of view. And the study focused on studies to increase the efficiency of OECs. Some of the studies on OEC efficiency that have been are as follow in this slide. So on the 2023, use research concerned with the basic modification in ground of the OEC on the chain one double cylindrical and others in the slide. The next interesting experiment on OEC efficiency optimization is on Selig and Pandev. In this study, OEC modified its underlip shape to improve efficiency, and surprisingly, this small modification is capable of improving efficiency quite satisfactorily with very small change. What's more, this change is quite simple. So to apply on the OECs that are already in the field is very possible. And the research submitted by Mandev, Selig discuss more about the result and outputs. But the hydrodynamic phenomenon and it is, are less expensive. So in our research, our study, CFD based, will be conduct on what is actually happening inside the OEC column, so that efficiency can be increased with the data of this research reference experiment of Selig. And then the material and methods in our research is based on CFD. So in this case, for the first solution related to the governing equation, in this slide, the governing equation is mass conversion equation and then momentum conversion equation. And in the meantime, to calculate efficiency, we need to count our inputs and outputs, where with the following equation like this slide. And then for material and methods, variable that are used in modification of the form complete, the form that are mean around the case, and then quarter circle case, front semicircle case, back semicircle case, and circle case like in this slide. And the wave characteristic for testing is height of wave is 0.07 meter, and then period peak of 1 second, and steepness of 0.02. And the wave steepness of this n dimension like in this slide. Then the first step to the simulation is the creation of the geometry of the domain for simulation. So we use the ANSYS space claim software with the following like this. The next step in CFD is a meshing setup, followed by the meshing that has been used in this CFD like in this slide. And for the skewness and orthogonality to be assessed accordingly, then set up the simulation model. So this is the setup simulation in software file. Transitional data reveals so that transitional model activation is, and for the material, cell zone dynamic mass, boundary condition, the report definition, initialization calculation, and output animation can be read in this slide. So next, this is the mass independence used where the crucial area is varied sizing. From the result, obtained that the best value where the size of the grid affect the result of the simulation. 3 millimeter is used on the crucial area for sizing grid, and after conducting the mass independence test, it is further validated with clinical research since this study has the greatest deviation of 5%, then it considered valid. Then this is the example result of the animation. We looked at in this zone. This is residual graphic. This is velocity graph, and this is the animation. Next. So the data obtained from the ANSYS is the speed and absolute pressure data. This data is used to calculate the power, and from the data, the underlift modification is capable of improving efficiency, and the biggest increase in efficiency was in a modification of underlift, that circle case model, so with an increase of 8.86%. I mean, we'll to find out what's going on and how under modification can be able to improve efficiency is by using the blend. So uh, here are 6 turbulent kinetic energy units on each modified model. So the kinetic energy describe the loss of flow to turbulence on the underlip side. By the time water wave come, the underlip side of the conventional rectangular model had the largest turbulence, depth, largest turbulence compared to the other model. Yeah. And the modification was successfully in reducing the energy, so the efficiency was greater than depth of conventional underlip model. So this is when the wave back. Also, at the time of the resume wave, the modification was successful in reducing the turbulent kinetic energy on the side of the underlip, so that the efficiency is greater than the conventional. So this is my presentation about my research, and thank you for your attention. Wassalamualaikum.